Hello scholars, thanks for tuning in. What are we going to learn here? Number one, how do you use the equation F equals ma, otherwise known as Newton's second law? Number two, where does it come from? And number three, what does directly proportional and inversely proportional mean? So let's start by writing down the equation. Newton's second law. F net equals mass times acceleration. And let's look at the units for that. We know that mass is measured in kilograms. We know that acceleration is measured in meters per second square. When we multiply those units, we get units of kilogram times meter per second square. But we do have a special name for this. We call that a Newton. This equation can be written two other ways. It can be written A equals net force divided by mass. How do we know that? It's very simple. We can just take both sides of this equation and divide by mass. Mass goes away on the right, so we have acceleration equals net force divided by mass. And we could also write it mass equals net force divided by acceleration, where instead of dividing by mass up on top here, we can divide by acceleration instead. And we can do this as an algebra triangle, where we have mass times acceleration on the bottom and net force on top. And remember how these work. If we want to solve for the mass, that mass is net force divided by acceleration. Or if we wanted to calculate what is the net force, we can do mass times acceleration. And lastly, if we want to calculate what is the acceleration, we can do net force divided by mass. So let's take a look at an example. You can push this up out of the way. So let's say that we have a floor. Let's draw that. Nope. We want to get rid of that again. Let's scroll it up. Okay, let's try that again. New program. Okay, so we have a ground. We have a box sitting on the ground. We're going to come up and apply a force to it. And we're going to apply a force of, let's say, 12 newtons. We'll call it F applied equals 12 newtons. But there's going to be some friction there. So let's label that F of friction. And let's call that 4 newtons. So let's label this here. This is our example of how to use this equation. And what else do we know? Let's say that the mass of this box filled with your favorite food is 10 kilograms. And I might ask a question like, what is the rate of acceleration? What is the acceleration of the box? How can we figure that out? So we can go back to our equation for Newton's second law. Acceleration equals net force divided by mass. And I'm going to move this up a little bit here. And so we can do acceleration equals net force divided by mass. The net force is going to be 12 newtons to the right minus 4 newtons to the left. I'm going to put little arrows on there just to keep track of my directions. Divided by 10 kilograms. And what does this come to? 12 newtons to the right minus 4 newtons to the left leaves a net force of 8 newtons to the right. Divided by 10 kilograms. And that's going to give us 0.8 meters per second square. How do we get meters per second square? Well, you can think of it two ways. This is acceleration, so we know that acceleration has those units. And also newtons divided by kilogram. Remember that a newton is a kilogram times a meter per second square. So the kilograms will just cancel out. Okay, so that's the example I wanted to do with you. And I want to talk a little bit about where this equation comes from. So let's check out the next. So back in the day, Newton really was the man. Aristotle, 2,000 years before him, was thinking, what's the deal with motion? Do things go in a straight line and then drop straight to the earth when you throw them? No, of course not. Do heavier objects fall faster? Well, only when there's some fluid resistance, like air resistance or water resistance. Galileo got the idea that, okay, I think maybe if things are in motion, they're going to stay in motion as long as there's no resistive forces. But Newton really took it to the next level. And what he did is he calculated the rates of acceleration. He measured the rates of acceleration on an object as different amounts of force were applied. And he saw that the relationship looked kind of like this, a straight line. That as the force increased from 1 to 2 to 3 to 4 to 5, that the acceleration also increased. So that you apply more force, you get more acceleration. Not only that, but he realized that if you were to double the force from, say, 2 to 4, the rates of acceleration, which is 1 here, also double. So going from 2 to 4 newtons of force caused the acceleration to go from 1 to 2. Double the force, you get double the acceleration. This has a name for it. It's called directly proportional. And I would like you on your paper to write down a definition for directly proportional. It is when changing one variable causes the other variable to change the same. When changing one variable causes the other variable to change the same. So you double one, the other one doubles. You triple one, the other one triples. So let's take a look at, let's say you have a hand pushing a brick. The force of the hand accelerates the brick. Okay, got it. And but what if you have twice as much force acting on it? Two hands. That will produce how much acceleration? So, for example, we will get twice as much acceleration. And we can look at this from a mathematical perspective, that if we double the force and we divide by the same mass, we're going to get twice the acceleration. It just makes sense that way. You double one side of the equation, the other side doubles too. Let's take a look at the other type of proportionality. It's called inversely proportional. And so he also did experiments where he used one force, but what he did was change the mass of the object that force was being applied to. And he found that the rate of acceleration changed. That as he used a heavier mass, as mass increased, he got less acceleration. So you can see here, if he had a mass of, say, 3 kilograms, he would have only been getting like, maybe 4 meters per second square or so. I'm not really using any units here. We're just looking at the shape of it more or less. But let's start with this data point right here. So we see that for that data point we are getting 10 units of acceleration. If the mass is doubled from 1 to 2, then reading over this, we are getting 5 units of acceleration. So when we doubled the mass from 1 to 2, we got half the acceleration from 10 to 5. And if we were to triple the mass from 1 to 3, then we would get 1/3 of the rate of acceleration. So let's take a look at some practice with that. So going back to the same hand pushing the brick. But what if the same force accelerates 2 bricks? It will accelerate them blank as much. What do you think the answer is? So if you said half as much, that is correct. And we can look at this again from this equation. When you double the mass, that means you are now dividing your force by a mass that's twice as much. So you're going to get a rate of acceleration that is half of what it was. Example here, what if you are pushing that same force on 3 bricks? You will get how much acceleration? If you said 1/3, that is correct. And again, same process, 3 times more mass, we're going to get 1/3 the rate. All we're really doing here is dividing both sides by 3. So the equation is still an equation, it's still true. So where are we going with this? We're going with this in a direction that shows how Newton came up with this equation in the first place. We now use it as this, A equals F net divided by mass. But when Newton was thinking of it, he was thinking of it this way, that acceleration, let me move that over, he was thinking of it that acceleration is directly proportional to the net force you apply to it. He wasn't really messing around with units. There was no unit called Newton back then. That came later, as people wanted to honor his work, his foundation. But he also found that acceleration was inversely proportional to the mass. And so we can combine these two together to say that acceleration is proportional to the ratio of force divided by mass, like that. But this little symbol, this little squiggly in there, that means is proportional to. And saying that two things are proportional is not the same as saying that they are equal. Proportional to. To say that they're equal, we have to just make sure that we're using correct units. So let me show you something here. We have acceleration. We can turn that into an equals force divided by mass as long as we are using units of newtons, as long as we are using units of kilograms, and units of meters per second squared. Only under those conditions can we say that this equation is actually an equation that works. Okay, so just a little insight there. So I'd like to come back to this slide for just a minute because we didn't really define what inversely proportional means. And I'd like you to write this on your paper. Inversely proportional means that when one variable changes, the other variable changes the opposite. So when the mass increases, the acceleration decreases. Or, conversely, if the mass decreases, the acceleration increases. Okay? And that's, again, in contrast to directly proportional, where as force increases, acceleration increases, does the same, whereas force decreases, acceleration decreases. So, last thing with you here, what if we have this situation, where we have twice the force acting on twice the mass? I think I gave the answer already. It will give you the same acceleration. Why is that? These factors are going to cancel each other out. Twice the force acting on twice the mass. We put a 2 in front of the force, we put a 2 in front of the mass, they cancel each other out, and we get the same rate of acceleration as we had before. So that one represents the same. Okay? So make sure you do everything that I'm asking you on EDU. A lot of little things to take care of. But I did assign a few practice problems from the book. They're pretty straightforward. I want you to do them though. I want you to get comfortable with using these units of newtons, kilograms, and meters per second square. And I'll see you guys in class. Thanks for tuning in.